Okay, question 4 says, in each part, match the parametric equations with one of the curves labeled 1 through 6 and explain your reasoning. Okay, so you see here for parts A through F, we're given parametric equations, and our job is to match each set of equations to the corresponding curves below. And for part A, we have that x is equal to the square root of t and y is equal to the sine of 3t. And so to begin, I'm just going to sketch x and y as functions of t separately. So you see that x is equal to the square root of t in green and y is equal to the sine of 3t in blue. And note that from this curve for x, for t greater than or equal to 0, x is greater than or equal to 0. Okay, so that implies in particular that the corresponding curve in the xy plane lives on or to the right of the y-axis. Okay, and scanning through this list, the only curve that satisfies that condition is curve 4. We are on and then to the right of the y-axis. Okay, x is greater than or equal to 0. Note also that y is bounded between -1 and 1, and that is the case for this curve here. Notice also that as t increases, x increases, so that implies that we're moving to the right. And the rate at which we're moving to the right is decreasing because the slope on the square root curve is decreasing. And that's reflected in this graph in 4 by the fact that this coil is tightening up as we move to the right. All right, so A corresponds to curve 4. All right, now for part B, we have that x is equal to 2 cosine t and y is equal to 3 sine t. And so here are those curves. And now note that x in particular is bounded between -2 and 2, and y is bounded between -3 and 3. And so saying that the x and y coordinates are bounded is not quite enough to conclude which curve from this list corresponds to these equations. Because note that curve 1 and curve 2 are such that the x and y coordinates are bounded. Now it's a little less clear from curves 3, 5, and 6. For example, if I look at curve 3, it may or may not be the case, just looking at this picture alone, that the x and y coordinates are bounded. For example, this curve could continue in this direction indefinitely. Okay, so can't quite say that in that case. So we need to do a little bit more here. And so noticing that x and y are in terms of sine and cosine, like we saw in the last video, okay, the Pythagorean identity can be useful. So what does that say here? Well, cosine of t is x over 2, and so cosine squared of t is x over 2 squared. And likewise, sine squared of t is y over 3 squared. And see, this is the standard form of an ellipse centered at the origin with semi-minor axis equal to 2, that's right here, and semi-major axis equal to 3, that's right here. So we conclude that B corresponds to curve 2. All right, now as an aside, a slightly different way to argue why B corresponds to curve 2 is to note that curve 2 is the only curve in the list that does not pass through the origin. And see, if this curve were to pass through the origin, there would have to be a value of t that made both x and y equal to 0. And that is not the case here, and that's because sine and cosine are out of phase. There is not a value of t that makes both of these 0. Okay, so again, we would conclude that B corresponds to curve 2. All right, but in any event, let's go ahead and press on to part C. So for part C, we have that x is equal to t cosine t and y is equal to t sine t. All right, so here are those curves on their own. Okay, so going back to B for the moment, when I have something like x is equal to 2 cosine t, x oscillates here between -2 and 2, right? The amplitude of that cosine wave is 2. Now when I'm looking at something like t times the cosine of t, okay, this is going to oscillate similar to a cosine wave. However, this t in front is going to act as a variable amplitude. Okay, so we're going to oscillate in a way that's similar to the cosine wave, but this t is going to give rise to a growing amplitude of oscillation, and likewise for this curve for y. Notice also, right, since we have a cosine for x and a sine for y, like part B, there's a certain out of phaseness, so to speak. Okay, so keep that in mind. The other thing I want to point out here is that if I look at the Pythagorean identity, what does that tell me here? Well, now cosine of t is x over t, and so cosine squared of t is x over t squared, and then likewise sine squared of t is y over t squared. And if I multiply both sides of this equation by t squared, I get this relationship, that x squared plus y squared is equal to t squared. And see, this looks like the equation of a circle centered at the origin of radius t. But see, here you have to remember that t is increasing. So what this relationship really tells me is that the radial distance from the origin grows as t increases. Okay, so if we put all of that together, we are looking at curve 5, right? I'm spiraling outwards away from the origin. Okay, now here's an animation of that curve. So I just put in the parametric equations, and then here's a tracing point. So if I hit play, I see that this particle is spiraling away from the origin as the parameter increases. All right, very good. And now that leaves us with 3 left, right? We have D, E, and F. And D and E look somewhat similar. In particular, they don't involve trigonometric functions. Okay, so let's start with E, actually. Okay, notice for E, the equation for Y is such that this expression in both the numerator and denominator contain quantities that are always non-negative, right? I have a square on the t up here, so that's never negative, and 1 plus t squared, that's always strictly positive, right? So that says that y is greater than or equal to 0 for all t. Now, just like what we saw in A, okay, this condition implies that the corresponding curve in the xy plane lives on or above the x-axis. And looking through this list, curve 3 is the only curve that satisfies that condition, right? We are on and above the x-axis, and so y is greater than or equal to 0. So E must correspond to curve 3. All right, and then looking at D and E, well, notice for D, okay, I have a 1 plus t cubed in these denominators. So in particular, if t is -1, I'm going to have a division by 0. Okay, what if t is really close to -1? Like, let's say t is really close to -1, but just slightly larger. That's what this plus sign means, right? So in that case, x will be infinitely large but negative, and y will be infinitely large and positive. In particular, the big takeaway here is that x and y are unbounded. And so D cannot correspond to curve 1, because clearly x and y are bounded in curve 1. And since in F, right, these are both sinusoidal functions, right, x and y are bounded, we conclude that F corresponds to curve 1 and D corresponds to curve 6. All right, great. Well, that's going to do it for this video. Thank you so much.